Hi guys, in this video we are going to talk about the fossil fuels and carbon compounds. And in this video we are going to focus on the reaction with alkenes as well as the addition polymers. Alright, so let's get started. Okay, now for alkenes, first of all you need to recognize that the general formula is CnH2n. For those of you who don't want to memorize all those general formulas, all you have to do is actually to memorize the general formula of alkane. So for alkane, the general formula should be CnH2n plus 2. Okay, so how do we figure out the general formula of alkene from alkane? Actually, it's not very difficult. So first of all, I can use an example of an alkane. For example, I will use ethane. All right, ethane. Okay, so this one is obviously C2H6. Right, you can substitute 2 into this general formula, then you have the alkane, the ethane, right? Now, when we form the alkene, alkene is having the functional group CC double bonds, right? So if you want to form a CC double bond with 2 carbons, then the corresponding alkene must be this one, right? If you form a double bond, it will be the corresponding alkene. And this one is the ethene C2H4, right? Now, you realize that when you have to form a CC double bond from an alkane, you need to sacrifice 2 hydrogen atoms, right? You need to sacrifice 2 hydrogen atoms. So if you're looking at the molecular formula, from here to here, we have removed 2 hydrogen atoms, right? 2 hydrogen atoms, okay? Now, using the same idea, the general formula for alkane is, if I kind of make it bigger, the general formula for alkane is CnH2n plus 2, right? So CnH2n plus 2, if you minus 2 hydrogen atom, right? So you minus 2 hydrogen atom from here, so the plus 2 is cancelled out. Then we will have CnH2n, which is the general formula of alkene, right? So this technique allows you to actually deduce all the general formula for all the homologous series based on the general formula of alkane. So you don't have to necessarily memorize all the general formula, right? Now, so that's the idea. Now, another thing about alkene is that for all the alkenes, we will call them unsaturated hydrocarbons. Okay? Now, hydrocarbons, you know, is a compound consists of carbon and hydrogen only, right? For unsaturated, it means that for the simplest explanation, that means it has multiple bonds, such as carbon-carbon double bonds, okay? Multiple bonds. It can also be triple bond. For triple bond, that would be alkyne, right? So this is the simplest explanation of unsaturated or unsaturation. Now, if you want to study in a more detail or to be more precise, for unsaturated, that means we say that the carbon is not yet saturated with hydrogen atom. So again, if something that is unsaturated, it means that the compound, okay, is carbon is not yet saturated with hydrogen atom. Hey, what do you mean by saturated with hydrogen atom? If you look at this one, again, this is an alkene, right? So each carbon is connected to 2 hydrogen atoms. However, can the carbon attach one more hydrogen atom? Yes, it can. All it has to do is to convert the CC double bond into CC single bond. Then you will have 2 covalent bonds available to join with 2 extra hydrogen atoms. So this is the reason why we say that for alkene it is unsaturated, because it can still connected to more hydrogen atom, right? However, for alkane here, for this one, ethane, can the carbon attach to more hydrogen atoms? No, okay? So each carbon atom has attached to the maximum number of hydrogen atom possible. So in other words, it is referred to as saturated, okay? This is a more precise meaning of the saturation or unsaturation, okay? But for DSE, this is all you have to know. Okay? Multiple bonds such as CC double bond and CC triple bond, okay? Now, another thing you need to know is for alkene, they are reactive, okay? Now remember, alkane, okay, ANE, alkane is not reactive because they have a strong CH bond, okay? And it does not have a particular, it does not have an area where there are a lot of electrons, or there is an area where there is a significant partial charges. So this is the reason why alkane is not very reactive. However, for alkene, okay, it is reactive because of the high electron density and the CC double bond. So if you have a lot of electrons concentrated at the CC double bond, it will be more likely to attract something that is perhaps positively charged or partially positively charged to attack this area and resulting in reactions. Okay, so this is the reason why alkene is more reactive. Okay, so what kind of reactions do alkene usually take place? So we can have three reactions. The first of all is a combustion, and then we have addition reaction, and also addition polymerization. And we will break it down for you one by one in detail. Okay. Now the first one, combustion, like alkane also undergo combustion if the oxygen availability, okay, is sufficient, then it will undergo complete combustion, forming carbon dioxide and water as the major product. So for this reaction, some of you may memorize the general formula like this one, but for me, I'm not good at mathematics, so very often I will forget this general formula. But still, you can balance this equation easily. Just later, I will show you how to balance an equation, okay, involving combustion, okay, not necessarily requiring to use this general equation. But of course, if you can memorize it, it could be an advantage, okay. For incomplete combustion, with insufficient oxygen supply, that it will give carbon monoxide instead of carbon dioxide. It could also give you carbon, but usually we will state carbon monoxide being the major product in this case. Okay. Now, a couple of remarks. I'm not going to talk about it in detail. So first of all, when we try to compare alkane and alkene, when it comes to combustion, we say that alkene does not being burned or does not use as a fuel as much as alkane, right? In fact, very few fuels will involve alkene. Well, it does have some, but not many. There are a couple of reasons. The first reason is alkene is a very important reactant. It's a very important industrial feedstock for making other organic compounds. Simply because it is quite reactive, and later on you will know it can be converted into different homologous series. It can be converted to different compounds with different functional groups. So that's why it will be a waste to just burn it. All right, this is the first reason. The second reason is because the combustion of alkene actually produces less heat and also burns with a sootier flame. Okay, so that's why we are not using alkene as our fuel. Usually, we will burn alkane instead of alkene, right? Now, for detailed explanation, I'm not going to include here. If you're interested, you can ask me later. Now, let's talk about the addition reaction. Now here, please put many stars over here, because this is like very important part. Almost every year they will ask about this in DSE exam. okay, addition reaction. So if you remember, when we talk about alkane undergo substitution reaction, right? Substitution reaction. In substitution reaction, we say that part of the atom is replaced by another atom or another groups of atoms, right? So in a substitution reaction, you will expect to see A plus B forming C plus D, okay? This is a substitution reaction. Because what we are trying to do here is to replace the atoms or replace the groups of atoms, right? So it's like exchanging atoms. So therefore, two reactors react and then ends up with two products because they're just exchanging parts of their structure. Okay. Now, for addition reaction, this time we have two reactants or even later on three reactants add together. So for addition reaction here, we should expect to see A plus B forming C, forming a single compound, okay? Because they are added together. Okay? So this is the difference between substitution reaction and addition reaction. Now let's see how it undergoes the reaction. Now let's use this as an example. We have a couple of more examples, but let's just look at this one. Now alkene is able to react with hydrogen, okay? The name of this reaction is called hydrogenation, but the type of reaction is called addition reaction, okay? In this reaction, if you look at the equation here, this is an ethene molecule. It reacts with hydrogen to form ethane, all right? So you see, two reactants to form one single product, okay? So this is obviously addition reaction. Now, let me just sort of break it down for you how this reaction is taking place. Now, you can understand this reaction by, okay, thinking about the alkene molecules where it opens up the double bonds. Now, think about when it opens up the double bonds, then it becomes single bond, okay? Now, what is going on here is that there would be two covalent bonds available to attach to other atoms, okay? So what it is going to attach with is based on what products we have, what reactants we have. So in this case, we have hydrogen, right? So the hydrogen molecule, okay, I would put it this way. So one of the H will connect it to this carbon, another H will be connected to this carbon. So at the end of the day, we will have the ethane, okay? You can understand the reaction by thinking about the alkene open up the CC double bond with two covalent bonds, each on each carbon atoms available to be connected to the reactants. Okay, in this case hydrogen, then it will undergo it this way. Okay, now so one thing you need to pay attention is you notice each hydrogen atom is attached to one of the two carbons. So you won't expect to see two hydrogen atoms connected to the same carbon atom, despite they are all hydrogen atoms. But if we have a color to distinguish them, then the blue hydrogen, well, both of them are blue, sorry. The pale blue hydrogen atom should be connected to the carbon atom, one each, okay? So that's the idea. Okay, now there are a couple of remarks. Now starting from now, or actually when you learn about free radical substitution, you start to realize that in organic chemistry, we emphasize on the reaction conditions. We emphasize on the reaction conditions. For free radical substitution, you should know that it requires the exposure of UV radiation or heat in order to start the free radical substitution of alkane, right? So here, we also have some conditions needed to be fulfilled. Now here, we need to use a catalyst. Now there are two choices. You can have nickel or platinum. Now if you use nickel catalyst, then it requires a high temperature and a high pressure. Okay? However, if you use platinum catalyst, it does not require extreme conditions. It only requires ambient or room temperature and pressure only. So of course, I would recommend you guys to memorize platinum being the catalyst. Okay? Now a second reminder is that when you write down the chemical equations, now before you may use the molecular formula. Now what is molecular formula? You may use C2H6, something like that, or in this case C2H4. Okay? Now this is what we call the molecular formula, simply showing the atomic composition of a compound. Alright? These are called molecular formula. Okay? Before you may use this one to write the equation, but in organic chemistry, especially starting from now, whenever we have functional groups, okay, we cannot use molecular formula. We cannot use molecular formula. So please, building up a habit such that starting from now, when you are writing chemical equation involving organic compounds, try to use structural formula. Structural formula. Okay? This is structural formula because the structural formula tells you about the structure, especially the functional group. Okay? Try not to use this anymore. Okay? So here, alkene reacts with hydrogen to form alkane. So yeah, that would be my second remarks. Use structural formula. The third remarks here is this particular reaction has a specific application, which is to make margarine. Now, what is margarine? Margarine is plant butter. Okay. Now you know this one, butter, right? So from the Chinese name, you know it should come from cow, right? Cow. And for animals, they have fat instead of oil, right? And you know fat is a solid, okay? For plants, they have plant oil, which is a liquid, right? So what do you mean by plant butter? Plants should have a liquid oil, but animals should have a solid fat. So what is this one? It's kind of in between, right? I do think you have this experience before when you have a butter. A butter is essentially a semi-solid, right? It's a solid overall, but it's pretty soft. It's quite spreadable, and it kind of looks like a liquid, right? So the idea is, because the butter, if you are making it from animal's fat, it's quite expensive. So people is trying to make use of plant oil, and which is much cheaper, and convert it into something similar to butter. Now, to convert a liquid plant oil into a semi-solid margarine, they need to undergo a reaction called partial hydrogenation. Partial hydrogenation. Okay. Now, as to why partial hydrogenation can convert a liquid into a solid, in a very simple explanation is that this process can increase the melting point. Increase the melting point of plant oil. So think about it, when a liquid's melting point increases, they will more resembling to a solid. Okay? So this is how partial hydrogenation able to convert liquid plant oil into solid margarine by increasing the melting point. But as to how the melting point is being increased, I may not explain here. If you're interested, you can ask me later. Okay? All right. So continue with addition reaction. So the CC double bond can react with many reagents, not only hydrogen, but also over here hydrogen halide. Okay, HXC. So usually it is HCl, HBr. Usually HCl, HBr. So in this reaction, very similar to hydrogenation, it opens up the double bond, and then we add in whatever we have. In this case, one carbon will be having the H, one carbon will be having the halogen atom. Okay, so this is the idea. Okay, three This one reacts with halogens. Now, halogen here, usually it is chlorine, bromine, and iodine. Okay? So, in this one, we have a condition that you need to pay attention to. Usually, the halogen are used in gaseous form, or we dissolve them in organic solvent, such as CCl4. Okay? Now, in gaseous form, usually we are talking about chlorine, right? Because chlorine is a gas by itself. But bromine and iodine, usually we would dissolve it in organic solvent. Okay? Bromine, okay, and iodine. Okay? Now, the reason why we need to dissolve it in organic solvent is because for bromine and iodine, they are very toxic. And iodine is even a solid, if you recognize, right? So, iodine cannot be molten, cannot be melted into liquid, right? Iodine, when you heat it, it sublimes, right? So, a solid iodine doesn't really, convenient to be used to undergo a reaction. And for bromine and iodine, both of them are quite toxic, especially bromine. So we do not use pure bromine, despite it is a liquid by itself. We should first dissolve it into organic solvent, okay, so that it is much more diluted and therefore much less toxic. Okay. Bear in mind, in DSC, if you use bromine liquid, no marks will be given because this is too dangerous. It's not an appropriate procedure. Okay. Now the reaction very similar. Again, open up the double bond and then plug in whatever we have. Then we have a dihaloalkane. Okay. In this part, usually they will ask about the color change because halogens have their color, and when they react, they will form the dihaloalkane or haloalkane, and those are colorless. So you should expect to see the color of the halogen fade out or being decolorized as the reaction proceeds. Okay. Now, in this part, usually the student will struggle with the color of bromine and iodine, right? Especially in different physical states. So I kind of give you a remarks over here on the right hand side. Okay, try to bring back your memory. Now, bromine and iodine, right? So if they are in aqueous solution, okay, if this is dissolved in water, then bromine is brown in color. Iodine is also brown in color. In a very dilute iodine solution, it will appear yellow, but it's not very important. Okay. However, in organic solvent, okay, solvent such as just now the CCl4, then bromine should exhibit orange color, whereas iodine should exhibit a purple or violet color. Okay. So that's why when you are asked to describe the color changes, make sure you memorize the different color. And this also enables us to distinguish between bromine and iodine because in an aqueous solution, these two appears very similarly. Okay, so pay attention to that. Okay. Now, another remarks here is that if you use an aqueous bromine, or we call it bromine water, then there's still a reaction, but instead of forming a dibromoalkane, it will form a bromo alcohol. The reason is because the water can also participate in the reaction, so you kind of having this one. Okay, so if you are intended to synthesize or produce a dibromoalkane, then you must use bromine dissolved in organic solvent. Okay. Now, reaction 4 here is out of syllabus, but could be useful if you have memorized this, especially later on when we talk about organic synthesis. Then this is one quite useful reaction. Okay, so alkene can react with concentrated sulfuric acid in order to convert it into an alcohol. Okay, the step is a little bit complicated. There are 2 steps. One, you need to react with concentrated sulfuric acid. You need to heat it up, and then you add in water. Okay, you're adding water. Okay. So, but I will not emphasize too much on on this reaction because it's out of syllabus. So let's move on to the fifth one. Now the fifth one here again is some sort of marginal case. It is within the syllabus, but it rarely asks. So this one is the reaction with cold dilute alkaline potassium permanganate solution. You see a lot of weird conditions, but I will explain why. Now, for this reaction, now for those of you, you should memorize KMnO4 being a very strong oxidizing agent. So this reaction is essentially an oxidation of alkene forming dialcohol. Okay, but also the reaction, actually it's an oxidation reaction. Okay, forming dialcohol. This is how we put down the equation. Now we use a middle bracket O to represent the oxidation, because if you really want to put down the ionic equation, the overall ionic equation, it will be quite complicated. So we will put this one to represent the oxidation. Okay, thinking about the KMnO4 providing oxygen atom to the alkene for the oxidation. Now, you may ask, why do we have to use cold alkaline potassium permanganate? Now, the reason is because for acidified potassium permanganate, it is a very strong oxidizing agent. So once they form the alcohol, the permanganate ion may further oxidize the alcohol to form dialdehyde or even a dicarboxylic acid. So this is not what we want. That's why we need to control the extent of oxidation. To do that, instead of using acidified potassium permanganate, we use alkaline potassium permanganate. Also, we use a diluted solution as well as a cold temperature. All these measures are to prevent further oxidation of the diol. Okay, so that is the idea. All right. So now, so far we talk about addition reaction with different reactants. We can react with hydrogen, hydrogen halide, halogen, and here cold alkaline potassium permanganate solution. Okay. Now down here, again, very important part, frequently asked in the DSC exam, is trying to distinguish between alkane and alkene. Alkane and alkene. So there are two common methods. The first one is to add bromine water. Now, if you remember, alkene would undergo addition reaction with bromine water to form the bromo alcohol, right? And this reaction will result in a color change where the brown bromine water is decolorized, becoming colorless. Okay. Now, what about alkane? Now, for alkane, it is possible to react with bromine because we can have a substitution reaction, right? But we need to have diffusion of sunlight. You must have UV radiation. So that's why when we perform this test, it would be best if we carry out it without sunlight. So maybe in a dark room, all right? So this one can prevent the substitution reaction between alkane and the bromine, okay? So if no UV light is available, alkane cannot react, so the solution remains brown, okay? So that's the idea. Now you may ask, hey, sir, wouldn't it form bromo alcohol with bromine water? Should we use bromine dissolved in organic solvent? Well, yes, you can. You can always use bromine dissolved in organic solvent. But you may ask, hey, sir, then why are we using bromine water here? Wouldn't it form bromo alcohol, which is not what we want? Now, here, first of all, you are correct. If you use bromine water, it does form a bromo alcohol. Okay? But the question here is, are we making a dihaloalkane, or are we simply want to distinguish between the two compounds? Now, if you are simply trying to distinguish the two compounds, you don't have to care about what product being formed. As long as they can give you obvious observable change, that would be fine. Both bromo alcohol and dibromoalkane will be colorless, so both will result in a color change. So therefore, we don't have to care about whether it is dihaloalkane or halo alcohol. Okay, so make sure you know what you are going to do here. Okay, simply to distinguish between the two. Now, the second common method that we use to distinguish between alkane and alkene is to add acidified potassium permanganate solution. Again, alkene will have a reaction and therefore resulting in a color change, purple permanganate ion becoming colorless manganese 2 ion. Okay? However, alkane, since there is no reaction, the solution remains purple. Okay? Now, in the similar discussion, you may argue, hey sir, here, why is it acidified then? But here is alkaline. Did I mistype anything? Again, it depends on whether you are making the di-alcohol or are you simply want to distinguish the two compounds. In here, we don't actually care about whether we are forming a di-alcohol, di-aldehyde, or even dicarboxylic acid. We don't care, right? As long as it can give us a color change, then we are able to distinguish between the two. Okay? Plus the fact that if you use alkaline potassium permanganate, it will actually give you some dirty brown precipitate, which is actually the MnO2. Okay? If you try to do a test, you try to avoid forming any precipitate, which will make the cleaning process more tedious. Okay? So that's the idea. All right? Okay, so before we move on to the practice question, there is one more remarks. So this one, some of you may recall this one, benzene. Benzene is this one with a 6 carbon hexagonal ring and then with alternating CC double bond. Then you may say, hey, this one is an alkene, right? So it has CC double bond, so it would also undergo addition reaction. Well, it turns out it is not. Benzene is a special case. So benzene and its derivative, derivative means a similar compound of benzene or a compound derived from benzene. So you can think about the derivative may include a benzene with a methyl group, a benzene with a chlorine, a choral group, something like that. Okay, so benzene and its derivatives will not undergo addition reaction despite having CC double bond. The reason is because this alternating CC double bond system, or we call it the resonance system, okay, is actually providing extra stability to the molecules. Okay, so this one is very stable because of the alternating CC double bond. If it undergoes addition reaction, then this alternating CC double bond system will no longer exist. So at the end of the day, you will destabilize the molecule. So a molecules or any chemicals doesn't want to be destabilized, so they will be resistant to addition reaction. Okay? Think about if addition reaction does take place. Okay? Say for example, it reacts with chlorine, then they may form something like this, right? Right? And you see, do you still have the alternating CC double bond system? No. So this reaction does not occur, okay? Because this is unstable. Okay, this is stable. Okay? So that's the idea. Okay. So down here we have some practice question. So my suggestion is you pause the video, try to attempt this question. Question 1, 2, 3, right? We have 3 questions. Try to attempt those questions, and then once you finish it, resume the video and look for the explanation. Okay? Okay, I assume you have already attempted the question, so let's discuss. Now here, propene burns completely in plentiful supply of oxygen. Write a balanced chemical equation. Okay? Now first of all, propene, CH3, CH, CH2. Okay? Remember, try to use a structural formula. Okay, now you know this one is actually C3H6, right? Okay, so complete combustion reacts with oxygen to form CO2 and H2O. Okay, now I understand when you use the structural formula like this, it makes it more difficult to balance the equation, right? So now you can first write down the structural formula and then you balance the equation by looking at this one. Then that would be easier. So here, 3 carbons on the left, 1 carbon on the right. So we should have 3 over here. And then the next step, we check the hydrogen. So 6 hydrogen on the left, 2 hydrogen on the right. So I should put down a 3 here as well. Okay. Now then we check the oxygen. 3 times 2 plus 3 equals to 9. So this one will be 9 over 2. 9 over 2. But we cannot have fraction numbers, right? So we will put down, we will have the whole equation multiplied by 2. So it turns out to be 9, 6, 6, 2. Okay? Right? Okay. So did you observe how I do the balancing equation for combustion? Right? We always balance the carbon first, and then the hydrogen, and at the last, we balance the oxygen atom. The reason is because for oxygen atom, it is involved in 3 chemical species, whereas for carbon and hydrogen, they are only involved in 2 chemical species. So it will be easier to balance carbon and hydrogen first, and we leave the oxygen the last. That would be easier. Okay. Right, B. Why alkene is seldom used as fuel when compared to alkane. So I did talk about that. So the first reason is because alkene is useful feedstock. Feedstock means the reagent for industrial production. Useful feedstock for making many organic compound and polymer. Okay, this is the first reason. The second reason is, like I said, okay, alkene, okay, release less heat when burnt, or it will burn with sootier flame. Okay, so this is another reason why alkene is not used. It's not commonly used as fuel. Okay. All right. Okay, down here again, balancing equation for the following reaction: ethene with bromine. Okay, ethene here, bromine here, forming 1,2-dibromoethane. Okay, 1,2-dibromoethane. Okay, and then butylene reacts with dry hydrogen chloride gas. So butylene, dry hydrogen chloride gas to form a 2,3-dichlorobutane. Sorry, this one should be H because it's a HCl gas. Okay, like this. Okay. All right. So it's just a 2-chlorobutane. 2-chlorobutane. All right. Okay. Now let's move on to this one. Looks like it is complicated, but actually it is not. Complete hydrogenation. Hydrogenation is the addition reaction with hydrogen gas. Now, you know, hydrogen can react with the CC double bond. So here we have 1, 2, 3. 3 CC double bonds. Now this one, CO double bond, does it react with hydrogen? The answer is no. So this one is not affected. It's not affected. Okay? So the reaction, we have this one, just copy it right away. Okay? reacts with hydrogen. Now, because we have 3 CC double bonds, so we need 3 hydrogen gas, and then forming a long hydrocarbon chain, saturated. So here, try to follow what I did here. So I try to match the carbon. Okay, this one, 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 this one. Okay, just like this. Now you can always double check. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so the number of carbon is the same. So that would be the reaction, the equation. Okay, now down here, so a few drops of acidic potassium permanganate solution were added to the sample of hexane and a sample of hex2-ene, and they are shaken well. And the diagram shows you the appearances of the 2 samples after the addition. So which one is hex2-ene, X or Y? Explain your reasoning. So there, of course, test tube Y will contain the hex2-ene. So you need to explain why. So first of all, we explain based on the observation because it changes from purple to colorless. Okay, but still you need to explain. Okay, so we'll explain with reference to the reaction that has taken place. So we will say only hex2-ene has CC double bond, which undergoes addition reaction with the KMnO4, but it would be best if you also talk about the color to form colorless products. Okay, so here you talk about only hex2-ene has CC double bond, so it can undergo addition reaction to form with the purple permanganate to form colorless products. Okay, you can say addition reaction or you can say redox reaction. Okay, both are acceptable, redox or addition reaction. Okay. Now, suggest another chemical test to distinguish. So instead of using permanganate, we can add what? We can add bromine water. Bromine water. So only hex2-ene changes from brown to colorless. Okay? Now this time we don't have to explain by talking about the CC double bond because the question simply asks you to suggest a test and give observable changes. Okay? So that's the idea. Alright? So that's the end of the alkene. Okay? So let's quickly move on to the addition polymerization. Okay, addition polymers. Alright, so here, first of all, you need to understand what is the meaning of polymerization. So if you look at this equation, okay, you see this one is the polymer. And the polymer, you can tell, is made by several monomers. Okay, so the idea is a lot of monomers here, they are the building block, they are the basic unit, and they connected to one another repeatedly, and at the end, forming a large, long compound, which is what we call a polymer. Okay? So many monomers join together to form a long chain of polymer. Okay? And the process, the reaction is called polymerization. Okay? So that's the idea. Now, remember, monomers are usually molecules, small molecules, and polymer, even though it is very, very large, it is still a molecule. We will still consider it as a molecule. So think about it as a huge, long molecules. Okay? So this is the reason why polymers, all of them are solid. All of them are solid. Okay? Because of such a big size, the intermolecular force would be very strong. Okay? Now here, we say alkene or other unsaturated compounds are able to form polymers. Especially for alkene, it can undergo a process called addition polymerization to form addition polymer. Now, so polymerization is a huge category of reaction. It's a huge category of reaction. Under polymerization, we have addition polymerization. And later on, we will learn about another type of polymerization we call it condensation polymerization. So think about it as two types of polymerization. And here, we will be focusing on addition polymerization. Okay? And in fact, a lot of plastics are actually addition polymerization. Okay? Sorry, addition polymer. A lot of plastics are addition polymer. Okay? Now, here, look at this equation. So this equation describes how addition polymer is formed from its monomer by addition polymerization. Now here, the monomer is called ethene. Okay, so we have the ethene molecules joined together to form a polymer, and we call it polyethene. Okay, so there are a couple of things, step by step. So first of all, I want you to know the name. Right? So the monomer are usually the same name as what we usually name the organic compound, the IUPAC systematic naming. Okay, usually it is the same. So the monomer, this one is ethene, so it's called ethene. Now the polymer is actually very simple. You just use the name of the monomer, and then you add the prefix poly. Then that would be the polymer. Okay? Now pay attention. Even though it is called polyethene, you should no longer see any CC double bond in the compound, in the polymer. Okay? So now this is the first thing, the name. Okay? Ethene to polyethene. Alright? Now the second thing, so I want to illustrate to you how this is possibly taking place. Actually, the idea, I used the empty space down here. The idea is very similar to addition reaction. So think about it. When we have an alkene, okay, so the alkene is able to open up the CC double bond. So it will become something like this. And you know, in addition reaction, if we have hydrogen, if we have like chlorine or whatever reactant it is, it can be attached to the carbons at these two areas, these two positions. Okay. However, in the addition polymerization, we don't have any other reactants. What we have is only ethene, right? So chances are there is another ethene molecule doing the same thing, opens up the double bond. So what do they do? So they will obviously join together. Okay? So that will form a 4 carbon molecules. Sometimes we call this one dimer, D-I-M-E-R, dimer, because we have 2 monomer units joined together, which is a dimer. Okay? Now, pay attention. For this dimer, you see, it still have 2 bonds available. So what you expect to see next is you will see another ethene molecules opens up the double bond, and what do? They just join to one another. Okay? And this is how they keep react and lengthening the chain. So that's the idea. This is how the reaction takes place. In fact, the actual reaction does not take place exactly like this. It actually involves a free radical chain reaction, but those details is out of the syllabus. So in DSE, you can think about the reaction like this. Okay. Now, so that will repeat. Then you may ask, hey, sir, to what extent the reaction stops? Well, it depends a couple of factors, but you know, this reaction is quite random, okay? So therefore, it is quite difficult to give you a very precise mole ratio relationship, right? I cannot like put down like 10 ethene to form like 2 polymers, each with 5 units. Well, it is quite impossible to describe it this way. Like I said, the reaction is quite random. So here, when we put down the equation, we will use N to represent. So N ethene monomers undergo polymerization to form one single polymer with N repeating units. So what is a repeating unit? Well, by its names, it means that if this repeating unit repeats itself, like you think about it, copy and paste, then if you copy and paste n times, then it will give you the polymer. Okay, so this one is an easier representation to show the structure of the polymer. Pay attention to here. Sometimes the question may ask you to show the structure of polymer. Sometimes they may ask you to show the structure of repeating unit. So the difference would be whether we have an N at the bottom right corner. Okay, repeating unit has no N, polymer has an N. Okay. Now, one more remark regarding repeating unit. So you may ask, hey sir, so I understand this one. When you copy and paste n times, then you will get the polymer. Okay, so can I choose this one as the repeating unit? Can I choose this one as the repeating unit? Because if this one I do copy and paste many times, I can still form the polymer. So can this one be the repeating unit? Well, it turns out no, this is not a repeating unit. No, not correct. The reason is because the repeating unit must show the structure of the monomer. And the monomer is ethene, right? So you need to show at least 2 carbons, right, with the ethene molecule. Okay, so you can't do this. Plus, if you choose this one as the repeating unit, then the polymer would requires 2N, right? So like this one and then 2N. This is not very convenient for us to show the concept. So that's why we don't do it this way. We stick with this one. Okay. So that's the idea. Now, before I move on, there's one question, or actually, I did talk about that just now. So the question is, like I said, it's quite difficult to know precisely how long the polymer is, right? It's not just like 6 monomers joined together to form a polymer with 6 repeating units. It's not like 100% every polymer molecule is like this. So we say that, okay, the polymer molecule do not have a fixed relative molecular mass. Okay, so that implies it does not have a fixed chain length. Okay, so but why? Why is that? So because we will say that this reaction, okay, because the monomers, molecules collide randomly to form the polymer molecule. Okay? So this is what I want to add, is that this reaction itself is actually quite random. The monomer molecules are randomly colliding with each other. Therefore, we don't expect to see a very fixed stoichiometric relationship, we don't expect to see all the polymers with the same chain length. But of course, in industry, they can adjust the reaction condition so that you will have expected range. I mean, you will have the product polymer molecules within an expected range of relative molecular mass or chain length. Because that one would affect the property of the plastic, the property of the polymer that you form. Okay? So that's the idea. Just one more reminder, guys. This is a very common mistake. So sometimes the question asks you to name the type of polymerization. And usually students will spell it as additional polymerization. So please, okay, when you do revision, do not spell it as additional polymerization, because this one must be wrong. It's addition polymerization. Addition polymer. Don't say additional polymerization. Okay? So just bear in mind. Okay, so let's move on to another practice question. So please, again, pause the video, attempt the question, and then resume the video for the explanation. Okay, let's do it. Polypropene. So first of all, propene. So for some reason, I will draw it this way for the propene. So we have N of them. Okay, reacts to form the polypropene. Make sure you have an N here. Okay, all right. Okay, now down here, so you are trying to identify the repeating unit and the monomer from a short section of the polymer. Okay, so this is basically to identify the repeating unit. So here, this one should be the repeating unit. Okay, so CCFCl. Okay, now remember, don't put down the N. If you put down the N, then it would be the polymer. Okay. Now the monomer, all we have to do is to give it back the CC double bond. So just like that. Okay. All right. Here. So this one, very similar. We have the repeating unit here. So okay, this is the repeating unit, and the monomer would be this one. Okay. Now this one, complicated, so ugly. But don't worry, we need to look for the repeating unit. So if you pay attention to, this one should be the repeating unit. Okay. So this chunk of thingy is put on the side. So we focus on the CC here, the CC double bond. Okay. So the repeating unit is like this: C double bond O CH3 H H H. Okay, like this. Then the monomer. All we have to do is to put down the CC double bond. Okay, just like this. Okay, the last one could be challenging because, again, this kind of representation usually is, you guys struggle with this representation. Okay, so the repeating unit is here. Okay. And here, the monomer is actually like this. Okay? Now think about it, like all these are the carbon, right? Okay, so this part corresponds to this part, okay? And then this part will be this part, okay? So that's the idea. Okay? Now, for page 58, this is the very common addition polymer. For this one, you need to know the name, you need to know the structure, repeating unit, monomer, all these things. And you also need to know the very common daily life application, because there could be a multiple choice asking, okay, which of the following polymer is commonly used to make, let's just say, PVC, sorry, not PVC, I already say. Let's just say to make disposable lunch boxes. Which polymer do we normally use? So you need to memorize these. Now, these are the syllabus required polymers. Now let's start with polyethylene. Now polyethylene is the basic one, made from ethene molecules. Now there are two types. We have low density and high density. So the difference is the chain, whether the chain has a lot of branch chain or side groups. Okay. Now, actually, I can show you with this diagram on next page over here. So if you look at page 59, so you see two diagrams. Now you see the one on the right hand side, you see the chain has a lot of branches, right? And the one on the left, you see there are almost no branches. They are all straight chain, just coiled up a little bit. Okay. Now, if it has a lot of branches, then the polymer molecules is less likely to pack very close. In other words, the polymers are packed loosely, leaving a lot of empty space between the chains. On the other hand, if you do not have a lot of branch chains, or you doesn't have any at all, then the chain is able to pack very close to one another. When you pack very close, then the density will be higher. Here, the density will be lower. So that's why this is what we call LDPE, low density polyethylene. Here, HDPE, high density polyethylene. Okay? So that is the difference between the two. Now, with the low density one, with more branches, they will be lighter, flexible, lower melting point. Usually they are used for making the plastic bags. You know, you go to the supermarket, you have to spend 50 cents on those. Now, HDPE with a higher density is harder and therefore can be used to make juice bottle, toys, okay, which require certain strength. Okay. Now, for polypropene made by propene molecules is stronger than polyethylene, have a little bit higher melting point, can be used to make storage boxes, car bumpers. Okay. Now, very recently we talked about the face mask, right? Usually with 3 pies, okay, 3 layers. So actually the middle layers is made by the polypropene, but they kind of sprayed it in a very fine fiber, forming a network with a very small pores that is able to kind of block away those particles. So yeah, another application for polypropene. Polystyrene, here the molecules, the monomer is called styrene, which is actually an ethene, but with one H replaced by a phenyl group or benzene ring. Okay, we have 2 types of polystyrene. The regular one is used to make transparent bottles. Now, because for these polyethylene and polypropene, they are usually white in color or they are quite opaque, translucent. I mean, basically not transparent. Okay, but polystyrene is transparent, so it could be used to make transparent plastic bottles. Now, the expanded polystyrene is what we usually come across when you order takeaway, because those takeaway disposable lunch boxes is made by expanded polystyrene. So what they do is, when they make the polymer, they introduce hot stream of air forming a lot. So when the polymer is fixed, they trap a lot of air inside the polymer matrix, therefore allow it to be very light, and then with a very good insulation of heat. So this is what you want for disposable lunch boxes. Light and able to keep the food inside warm. Okay. Now PVC, polyvinyl chloride, actually the monomer is vinyl chloride, also known as chloroethene. But we call it vinyl chloride. Again, we have two types. The regular one is hard, brittle, most importantly, resistant to corrosion. So usually for water pipes or any pipelines that is supposed to be installed outdoor, where it's commonly exposed to the rainwater or the atmosphere, right? Okay. Now we can also add the plasticizers. The plasticizers actually is some kind of small molecules that is located, that is basically spacing out the polymer chain. Basically make the monomers less closely packed, therefore make it more flexible, more elastic, right? Because if they pack very closely with a strong intermolecular force, they tend to be hard, okay, and brittle because relative motion are hindered when they are packed very close. But with plasticizer, those plasticizers space out the polymer chain, allowing certain extent of elasticity and also make it more flexible. Okay, a couple of years ago, you also heard about plasticizers being added into the bubble teas in Taiwan. Okay, that is the same thing. Okay, the curtain and raincoat, that would be the application with plasticized PVC. Okay. Now here, Perspex or the polymethyl methacrylate (PMMA). This one is what we usually call as the plastic glass. So the traditional glasses is made by the glass. The glass has a couple of disadvantages. Okay, being heavy and also very brittle, very easy to break. Especially before the contact lenses. The contact lenses are made by glass, so you can tell how dangerous it is when you have some sort of impact and the glass kind of shatters inside your eye. Not a good idea for your eyeball, right? But now, all the contact lenses, they are made by Perspex. So they are less brittle and lighter, so that it will be more safer for contact lenses, okay? Now, for Perspex, the advantages is they are highly transparent, just like glass, and also have high refractive index. So, in order to be the spectacle glasses for correcting short-sightedness or long-sightedness, you need to have a certain, you need to choose a material that is highly transparent and has a high refractive index. Otherwise, your glass will be extra thick if it does not have a very high refractive index. Okay, so that's the idea. Please spend some time to memorize these. And the last page is not something new. Actually, the physical property of addition polymers, like I said at the very first place, all the polymer molecules, like I said, molecules, right? So the physical property is governed by the strength of intermolecular force. So their properties are all based on the strength of intermolecular force. The first one is the chain length, which is essentially equals to the molecular size. So the longer the chain length here, the stronger the van der Waals force between the polymer chain. So this is easily understood. But as the chain length increases to a certain point, the increase of melting point is not that significant, kind of level off. Okay, that's the idea. Now the second one, I just talked about it, the branching, right? Using LDPE and HDPE, you will understand, with more branching, then the melting point should decrease because the polymer is having a lower packing efficiency. Okay? And the third one is obvious, the type of intermolecular force. So it depends on the monomers, whether they have non-polar side group or polar, electronegative side group or polar side group, or even side groups that is able to form intermolecular hydrogen bond. Of course, the one can form hydrogen bond should have the strongest intermolecular force and therefore highest melting point. Okay, so this should not be too difficult, right? So now that's the idea about the addition polymer. So that would be the end of this chapter, and this also concludes today's lesson. So stay tuned for another video. So see you guys later. Bye bye.